How vaccines train immune memory. A vaccine can turn a brief encounter with a harmless clue into a defense that remains ready for years. Imagine meeting a dangerous germ for the first time, but your immune system already has a wanted poster, a recognition plan, and specialist cells ready to respond. That is the central idea of vaccination, preparing the body's defenses before the real threat arrives, without making you endure the full disease. Vaccines train the immune system by showing it an antigen, a feature that the body can recognize as belonging to a particular germ. Depending on the vaccine, this may be a weakened or inactive germ, a harmless piece of it, an inactivated toxin, or genetic instructions that let cells briefly make the antigen. The immune system then builds a targeted response and stores some of what it learned as immune memory. The body's defenses have two linked branches. The innate immune system reacts quickly and broadly to signs of damage or invasion. It can create inflammation and recruit cells that swallow unfamiliar material. The adaptive immune system responds more slowly at first, but can target particular antigens with remarkable precision. Vaccine material is taken up by immune cells and displayed to lymphocytes, specialized white blood cells. This begins a coordinated response involving B cells and T cells, often in lymph nodes, the small immune hubs found throughout the body. Some B cells become plasma cells, which act like antibody factories. Antibodies are proteins shaped to attach to a specific antigen. By binding to a virus, bacterium, or toxin, they may block it directly or mark it for destruction by other immune cells. The first response takes time because the rare matching cells must be found and multiplied. After vaccination, some antibody-producing cells can continue releasing antibodies, while memory B cells remain ready to restart production quickly if the antigen returns. T cells add another layer. Helper T cells send signals that guide and strengthen other immune responses, including the work of B cells. Killer T cells can recognize and destroy infected body cells, which matters for germs that hide and reproduce inside cells. Not every vaccine stimulates each part of immunity equally, and antibodies are not the whole story. Protection can come from several overlapping defenses: antibodies that prevent infection, immune cells that limit spread, and memory cells that help stop an illness from becoming severe. Immune memory is powerful, but it is not identical for every disease or person. Protection may last for years, decades, or sometimes a lifetime. In other cases, it fades. Additional doses can strengthen a first response, improve the quality of antibodies, or refresh memory after it weakens. Some vaccines also need updating when a fast-changing virus alters its antigens. Even a well-matched vaccine does not create perfect protection in everyone. Age, health, the vaccine type, and the germ itself can affect the response. Immunity also takes time to develop, so protection is not immediate. A useful way to picture vaccination is not as an invisible shield, but as a rehearsal. The rehearsal cannot predict every detail of the real performance, yet it gives the immune system recognizable targets, practiced communication, and experienced cells. That is why a vaccinated person may still become infected while having a faster response and a lower risk of serious disease for many vaccines. Vaccines train immune memory by safely presenting a biological clue, triggering B cell and T cell teamwork, and leaving long-lived defenders prepared to act. The needle, drop, or nasal spray lasts moments. The lesson can last far longer.